Hello. Today I'll be proving that there is a alternate equation to derive perfect numbers, and here's how I'm going to be doing it. So we know that a perfect number is basically a number that simply adds that simply adds all of its factors to in order to create twice of that of itself, right? So 15 would be equal to something like 5 plus 3, and then plus 1 plus 15, because they're all its factors, and that's going to be equal to 24, right? But that's not a perfect number because that's not equal to 30. Now, see, when you try to add up all these factors, right, what you're gonna find is that all of these factors are always gonna be resulting from combining prime factors, which are basically prime numbers that make up other numbers by multiplying other prime numbers, such as itself or like some other prime number, like 3 times 5 times 7. And any number in existence can be made up of them, except for other prime numbers, because, well, that's the definition of a prime. Now, when we define a number like that, we use notation for that. So like 3 to some power p, right? 3 plus 5 to some power p5, right? Well, no, not times 5 to some power p5. Now, when we do this, we combine them in a way, because the amount of factors a number has is just equal to the amount of unique factors multiplying each other. Now, what do I mean by this? Okay, so let's say we have, say, some number, I don't know, n, right? N is equal to 3 times 3 to some power p, right? 3 times 5 to some power p5 times 7 to some power p7. Now, the amount of unique factors this number has, which have to be added together, is just equal to p3 plus 1 times p5 plus 1 times p7 plus 1. Now, why is that? Well, think about it like this. For your first choice of factors, we could choose either no threes, 1 3, 2 threes, 4 threes, all the way up to p to, subscript 3 amount of threes to multiply as, right? And then for p5, we repeat the same thing. And as for y, it's plus 1. It's because we also have to include a 0 in order to exclude it, right? And that's the amount of unique factors. And see, the reason why this is important is just because, okay, let's do something like this. Let's say we have 3 to the power of 4 plus, actually 4 might be a bit too big, hold on. 3 to the power of 3 plus 5 to, well, not plus, why do I keep messing this up, hold on. Times 5 to the power of 3, right? Now, what you're going to notice is that, okay, let's just make all the factors, and we will start noticing a pattern. So 1 times 5, right? Okay, that's no threes. 3 times 5, okay, 1 3. Now 9 times 5, okay, 2 threes. And then we have 27 times 5. Okay, now what you're going to notice is that they all share the same factor, right? And what's important about that is just that, well, since they all share the same factor, we can just add them up, right? So we just add them up. So 1 plus 3 plus 9 plus 27, times 5. Okay, now what's that going to be equal to? Well, there's actually an equation that you could find to derive it, which is n, well, okay, firstly we find maximum power of 3, right? Which in this case it's 3. So we find the base, the power, plus 1 minus 1 over the base minus 1. And what you're going to find is that this is going to be equal to 3 to the power of 4 minus 1 over 2, which is equal to, hold on, let me get a calculator here. All right, over 2. And what you're going to find is that that's going to be equal to 3 to the 4th power, right, minus 1 divided by 2, is that it's going to be equal to 40, okay? And when you add them all up, 1 plus 9 plus 3 plus 27, right, it's going to be equal to 40. So it's equal to 40 times 5, right? And, okay, so we know that that's equal to 40 times 5. But what about every other power of x, okay? So we have 1 times 5, 25, 3 times 25, and 9 times 25, 27 times 25, and 1 times 125, 3 times 125, 9 times 125, and then 27 times 125. Now, what you're going to notice here is that, okay, we can gather all the 3's into that equation, but how are we going to add all the 5's? Well, the answer is actually pretty simple. Oops, I missed that. We gather them all up, right? And now they all share the same factor of 40, and now we could just add them. You know, 5 plus 25. Oh yeah, I've got 1 times 3 times 1, 3 times 9 times 1, 27 times 1, 1 times 1, right? You're going to have 1 plus 5 plus 25 plus 125, and then it's going to be 40 times 5 to the power of 4 minus 1 over 4. And that's going to be equal to 5 to the power of 4 equal to 156. Now 40 times 156 is equal to 6240, right? And okay, now that we have that, now let's add them all together. Okay, 5 plus 15 plus 45 plus 27 times 5. Okay, 5 plus 15 plus 45 plus 135. Okay, 200. And then, well, okay, so then plus 40, because that's going to be that divided by 5, plus 1,000, plus 5,000, right? We're just multiplying by powers of 5 here, because that's exactly what we're doing here. And we're going to get 6,240. Oh, wow, won't you look at that? It's the exact same thing. Anyways, now that we've proved that these powers can be added together, we can now equate it to the prime factored version of the powers, right? Huh. Why is this not working? That's odd. Okay, got it working again. Freeform is so annoying to work around. Anyways. Alright then. Now, okay, what the hell is going on? Anyways. Now, we're going to equate it, okay? We are going to equate it. Now, I'm going to flip my iPad into Alpha because it's going to be a long equation. So, okay. So, let's just say some power A, right? No, some base A to some power right? PA times B PB times C PC blah 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 is equal to, and then we got this massive equation, right? APA plus 1 minus 1 over A minus 1 times A, no, not A, B, PB plus 1 minus 1 over B minus 1, and then dot dot dot, and they're equal because in order for it to be a perfect number, they have to be. The sum of all their factors must be equal to the multiplication over there. Now, of course, looking at it, we can't really just clear this out, right? These guys are unfactorable. So what we're going to do is we're going to move it to the other side. We will simply ignore that problem. So A minus 1 times B minus 1 times C minus 1 dot 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 times A PA times B PB times C PC, right? And it's all gonna be equal to APA plus 1 minus 1 times B PB plus 1 minus 1, right, times C PC plus 1 minus 1, blah blah blah. It goes on for every single factor you get. And what you're gonna get is, okay, well, this still doesn't really tell us anything, but it gets really interesting when you factor out the main number itself. Actually, no, we won't be doing that. But we know that A minus 1, right, B minus 1 and such can't be equal to that because, okay, so I'm just trying to think of a way to prove they're not equal to each other, because we don't really prove anything by removing it, don't we? Oh yeah, I forgot, that's actually 2 times that, because when you add up every factor, you also include the number itself, so we gotta include a 2 in there. Okay, let's just assume that we're trying to make both sides equal. All right. Say, if I were to factor out the original number, then we're not really proving anything here, are we? Because all we're proving is that those factors aren't equal to this, which we could, well, already tell. So what do we do here then? Well, I guess that'd be the end of this episode. Thank you for watching, and I guess I'll try to figure out something in the meantime.